Right now, at this exact moment, a golden mirror the size of a tennis court is floating 1 million miles from Earth, pointed at a single dim star in the constellation Leo. That star is so faint you could stare at Leo your entire life and never notice it. But the machine watching it is not looking at the star. It is looking at the shadow of something crossing in front of it, a planet. A world 124 light years away that is roughly 8.5 times the mass of Earth and 2.5 times as wide. A world sitting in the narrow band of space where liquid water can exist, and a world where, according to a NASA-led study published in July 2025, water may not just exist on the surface. Water may compose a significant fraction of the planet's entire mass. Not a thin film of oceans like Earth, not a few percent, possibly tens of percent, an amount of water so vast we do not have a good comparison for it anywhere in our solar system. The planet is called K2-18b. And in April 2025, a team at the University of Cambridge announced they had found what they called the strongest evidence yet that life may exist beyond our solar system, detected in the chemistry of this planet's sky. Within days, headlines everywhere were asking the same question. Had we found it? Had we finally found proof that something is alive out there? But here is what those headlines left out. What happened next? The scientific fight that erupted behind the data. The molecule that was supposed to be the smoking gun for biology, turning up on a frozen, lifeless comet. And buried beneath all of that noise, a quieter discovery that in the long run may matter far more than the controversy. A discovery that makes K2-18b the single most important world outside our solar system for answering the question our species has carried for 200,000 years. Stay with me because by the end of this, you will understand exactly what the James Webb Space Telescope found, what it did not find, and why the next few years could rewrite our understanding of where life can exist. If you want more stories like this, where the science gets explained properly instead of stripped down into clickbait, subscribe now because we are just getting started. Let's go back to where this story actually begins. The year is 2015. A space telescope called Kepler is already past its prime, limping through an extended mission called K2 after 2 of its 4 reaction wheels failed. Its job sounds simple. Stare at a field of stars and look for tiny dips in brightness, the telltale flicker when a planet passes between its star and Earth. In practice, it is one of the hardest measurements in astronomy. The dimming a planet creates is like watching a streetlight from 10 miles away and trying to notice the moment a gnat flies across the bulb. Somewhere in that ocean of flickering data, astronomers spot something. A periodic dip in the light of a cool red dwarf star cataloged as K2-18. They designate the planet K2-18b, add it to a list of thousands of candidates, and move on. Nobody calls a press conference, nobody writes a headline. But this quiet little entry has 3 properties that will eventually make it one of the most studied objects in the sky. First, its size. K2-18b sits in a category called sub-Neptunes, worlds bigger than Earth but smaller than Neptune, a type of planet that does not exist anywhere in our solar system. We have rocky worlds, we have gas giants, we have nothing in between. The galaxy, it turns out, makes more of these in-between worlds than any other kind, and we understand almost nothing about what they are. Second, its orbit. K2-18b circles its star once every 33 days. Around a star like our Sun, that would place it deep inside a furnace, but K2-18 is a red dwarf, smaller and cooler and dimmer. At 33 days out, K2-18b lands squarely inside the habitable zone, the band of distance where temperatures allow liquid water to persist on a surface. Third, and this is the property that turns the whole story from interesting to extraordinary, K2-18b transits. From our vantage point across the universe, the planet crosses directly in front of its star. That alignment, that pure geometric coincidence, means we can do something remarkable. We can read the chemical fingerprint of its atmosphere from 124 light years away. Here's how that works, because once you understand this technique, every discovery that follows will land differently. When K2-18b passes in front of its star, a sliver of starlight filters through the thin shell of atmosphere wrapped around the planet before continuing its journey toward us. Every molecule in that atmosphere, methane, carbon dioxide, water vapor, anything, absorbs starlight at specific wavelengths. Each one leaves its own unique shadow in the spectrum. If you can catch that starlight and split it apart with enough precision, the missing wavelengths tell you what chemicals that light passed through. Think about what that actually means. Light that left a small red star in Leo around the year 1902 before anyone alive today was born, traveled for over a century through empty space, grazed the sky of another world for a few minutes, picked up the chemical fingerprints of an alien atmosphere, and then continued until it landed in a telescope built by human hands. Written inside that light in a code made of shadows is the recipe of another planet's air. That is not science fiction. That is a measurement we can make right now. In 2019, the Hubble Space Telescope took the first real look, and a team announced they had detected the signature of water vapor in K2-18b's atmosphere. It was the first time water had ever been reported on a habitable zone exoplanet. The planet went from a footnote to a headline, but Hubble, extraordinary as it is, was never designed for work this precise. Its instruments could only see a narrow band of the light, and some researchers argued the signal might not be water at all. It might be methane mimicking water's fingerprint. The data was not sharp enough to settle the debate. To crack K2-18b open, humanity needed a sharper instrument, and on Christmas morning 2021, that instrument left Earth on top of a rocket. The James Webb Space Telescope is the most ambitious scientific instrument ever launched. A gold-coated primary mirror over 6.5 meters wide, folded like origami inside its rocket fairing, deployed segment by segment in deep space, then chilled to operating temperatures colder than anything in your kitchen by a sunshield the size of a tennis court. It cost roughly $10 billion and took 25 years to build. Hundreds of mechanisms had to deploy in perfect sequence 1,000,000 miles from any possibility of repair. Every single one of them worked. In 2023, a team led by Niku Madhusudan at the University of Cambridge pointed Webb at K2-18b. The results, published in the Astrophysical Journal Letters in September 2023, cut through the fog that had surrounded this world for years. Methane, detected at 5 sigma confidence, the gold standard. Carbon dioxide, detected at 3 sigma. It was the first time carbon-bearing molecules had ever been confirmed in the atmosphere of a habitable zone exoplanet. But what the telescope did not find may have been just as important: almost no ammonia. And that absence is a chemical clue. If K2-18b were simply a ball of gas all the way down, a miniature Neptune, ammonia should be present in its upper atmosphere. Something beneath that sky seemed to be scrubbing it out of the air. One of the leading explanations is as elegant as it is strange: an ocean. A vast, planet-spanning ocean of liquid water sitting beneath a hydrogen-rich sky, silently dissolving the ammonia out of the atmosphere above it. Scientists have a name for this kind of hypothetical world: a Hycean planet. Hydrogen plus ocean. A world with no continents, no islands, no land at all. Just water stretching from horizon to horizon under an alien orange-red sky. Now stop and sit with that for a second. Try to actually picture being there, or rather floating there, because there is nowhere to stand. The star above you would hang swollen and crimson, bathing everything in a permanent amber twilight. Gravity would pull on you with more than twice the force you feel sitting in your chair right now. And beneath you, instead of the few miles of ocean we know on Earth, there could be water plunging downward hundreds of times deeper than our deepest trenches, into pressures and temperatures where water itself becomes something alien, something exotic, something no submarine on Earth could survive. But here is the part of this that stops being abstract and starts being personal. Sub-Neptunes like K2-18b are not exotic oddities. They are the single most common type of planet in our galaxy. Our solar system just happens not to have one. If worlds like this can hold liquid water and support complex chemistry, then the number of potentially habitable environments in the Milky Way does not just increase, it explodes, not a handful of Earth-like twins scattered across the galaxy. Billions of ocean worlds hiding in plain sight, orbiting the most common type of star there is. We do not yet know what that means for the likelihood of life, but the fact that we now need to seriously ask the question is itself a shift in how we think about our place in the universe. And buried in that same 2023 dataset was something else. A whisper, a faint, uncertain hint of a molecule called dimethyl sulfide. The signal was weak, far too fragile to claim anything definitive. Most of the community noted it and moved on. But Madhusudan's team did not move on. Because on Earth, dimethyl sulfide is not produced by volcanoes. It is not made by lightning or rock chemistry or ocean currents. On Earth, dimethyl sulfide is produced almost exclusively by life. By microscopic phytoplankton drifting in our oceans, that faint, briny smell you catch standing on a beach with the wind coming off the water. Part of that is dimethyl sulfide, the chemical breath of a living sea. So the team requested more time on the telescope. They pointed a completely different Webb instrument at K2-18b, one that sees in mid-infrared wavelengths between 6 and 12 microns, and waited for the planet to cross its star again. What came back in April 2025 sent shockwaves through the field. The new observations showed spectral features consistent with dimethyl sulfide or its chemical cousin dimethyl disulfide at a confidence level of 3 sigma, and the implied concentrations were not subtle. The data suggested levels thousands of times higher than anything measured in Earth's atmosphere. If the signal was real, K2-18b's ocean would not just be habitable. It would be teeming, saturated with biological output on a scale beyond anything our own seas have ever produced. Madhusudan, a scientist trained to measure his words carefully, called it the strongest hint of possible biological activity ever detected beyond our solar system. For a few days in the spring of 2025, millions of people genuinely wondered whether the answer had arrived. If you are the kind of person who wants space stories built on real data instead of hype, go ahead and drop a like on this video right now, because it genuinely helps this kind of content reach more people who would enjoy it. Now, before we go further, you need to understand what 3 sigma actually means, because this is where the story turns. 3 sigma means there is roughly a 0.3% chance the signal is a random statistical fluke. That sounds almost certain, a 99.7% confidence. But science has been burned by signals exactly this strong before. In physics and astronomy, the threshold for claiming a genuine discovery is 5 sigma, a probability of roughly 1 in 3.5 million that the result appeared by chance. 3 sigma results die all the time. They are the universe's favorite way of getting our hopes up. And within weeks of the announcement, the scientific immune system activated exactly as it is designed to. Independent teams around the world downloaded the publicly available web data and started pulling it apart. This is not sabotage. This is science functioning at its best. Extraordinary claims invite extraordinary scrutiny, and the scrutiny came hard. One team reprocessed the data using different but equally valid statistical methods and found that the dimethyl sulfide signal faded dramatically. In most of their analysis runs, it simply was not there. Another group, led by Raphael Luque and collaborators, ran the full set of web observations from all 3 instruments, NIRISS, NIRSpec, and MIRI, through a library of over 650 different molecules and found something uncomfortable. Other far more ordinary chemicals, simple molecules containing the same methyl building blocks, fit the spectral features just as well. At the precision Webb can currently achieve for this planet, dimethyl sulfide and something as mundane as ethane leave nearly identical fingerprints. Their joint analysis, published in Astronomy and Astrophysics in 2025, concluded there was insufficient evidence for the biosignature claim. And then came the twist nobody expected. In late 2024, Nora Henney and colleagues at the University of Bern published results in the Astrophysical Journal showing they had found dimethyl sulfide on Comet 67P/Churyumov-Gerasimenko, the frozen lifeless ball of ice and dust that ESA's Rosetta mission studied up close. It has since been detected drifting through the interstellar medium, the cold space between stars where nothing lives. Laboratory experiments even demonstrated it can form through pure chemistry under conditions resembling exoplanet atmospheres. No biology necessary. The molecule everyone had called a smoking gun for life turned out to have a perfectly credible non-biological explanation. By mid-2025, much of the astronomy community had reached a measured verdict. K2-18b had not met the burden of proof for life. Not yet. And if the story ended there, this would just be another cautionary tale about headlines outrunning evidence. But it does not end there, because while the world argued about one molecule, the telescope kept watching. And what it confirmed next is, in the long view, bigger than the controversy. In July 2025, a team at NASA's Jet Propulsion Laboratory led by Renyu Hu published results from 4 additional transit observations of K2-18b. This was not one group working alone. Multiple independent teams analyzed the same data side by side, each using their own atmospheric models, and then compared which conclusions survived regardless of modeling choices. The verdict from this new, sharper data set was unambiguous on several fronts. The methane is real, the carbon dioxide is real, and when the teams modeled what kind of planet could produce exactly this atmospheric composition, the answer was striking. K2-18b is a water world, not a dry ball of rock wearing a thin gas envelope, not a miniature gas giant, a planet so drenched in water that it could make up a massive fraction of the planet's total mass, with some estimates reaching into double-digit percentages. Stop and sit with that for a second. Earth, the blue planet, the water world of our solar system, is only about 0.02% water by mass. Everything you have ever seen, every ocean, every glacier, every thunderstorm, is a thin, damp film clinging to a ball of rock. K2-18b may hold water on a scale we genuinely do not have adequate language for. Oceans so deep they would dwarf our entire hydrosphere. Layers of exotic water compressed into states that exist nowhere on our planet, wrapped around a distant core. Renyu Hu's assessment was direct. K2-18b is our best chance to study a potentially habitable environment beyond the solar system at the present time. Not a maybe, not one candidate in a crowded field, the best chance we currently have. And on the dimethyl sulfide question, the NASA-led analysis was honest. They searched for the signal using several independent models. They did not find conclusive evidence. The whisper remains exactly what it has been all along. Tantalizing, unresolved, sitting right at the edge of what we can currently detect. Now, I promised honesty in this story, so here's the other side. A planet-wide ocean is only paradise if it is the right kind of ocean. The same models that allow a warm, habitable sea on K2-18b also permit darker outcomes. If the planet's clouds do not reflect enough starlight back into space, the surface could run too hot. Instead of liquid water, the ocean could exist as supercritical steam, a crushing, scalding state of matter that is neither liquid nor gas, hostile to any chemistry of life we understand. Some researchers argue K2-18b might not have a true surface at all. Others suggest the Hiccean interpretation itself may be wrong, and that a simpler mini-Neptune model with no ocean explains the data just as well. And looming over everything is the star itself. Red dwarfs are notorious for violent flares, blasting their planets with radiation. Whether life could take root and hold on under that kind of sky is one of the biggest open questions in modern astronomy. So, no, we have not confirmed a habitable planet. What we have confirmed is something science has never possessed before: a world in the habitable zone with an atmosphere we can actually read, carbon chemistry we have actually measured, and a massive water inventory backed by real data from multiple independent analyses. Every previous candidate for habitability was a guess based on size and orbital distance. This one we can interrogate molecule by molecule, transit by transit, and that is why what happens next matters so much. Right now in 2026, K2-18b remains one of the highest priority targets on Webb's observing schedule. Every time the planet crosses its star, there is another chance to catch that century-old light and extract more information from it. The Cambridge team estimated that roughly one additional day of telescope time could be enough to either push the dimethyl sulfide signal to 5 sigma, the gold standard for a confirmed detection, or kill it for good. Either outcome would be historic. Think about that. We are living in the first moment in our species' entire existence when the question, is there life on that planet, is no longer philosophy. It is a measurement. A measurement with a schedule, a price tag, and a machine already in position to make it. And Webb will not be working alone for long. The European Space Agency is building Ariel, the atmospheric remote sensing infrared exoplanet large survey scheduled for launch in 2029. Ariel will survey the atmospheres of roughly 1,000 exoplanets, building the kind of statistical picture no single target study can provide. And NASA is developing the Habitable Worlds Observatory, a next-generation flagship telescope planned for the 2040s whose entire purpose is written into its name: to directly image nearby planets and search their light for the signatures of life. K2-18b is the rehearsal. It is where humanity is learning, molecule by molecule, mistake by mistake, how to read an alien sky correctly so that when the day comes that a signal appears and survives every test thrown at it, we will know exactly what we are looking at. No ambiguity, no argument, just an answer. Here is what I want you to carry with you. When the dimethyl sulfide claim started to crack under scrutiny, some people called it a failure, an embarrassment for the field. It was the opposite. A 3 sigma hint was reported openly. The entire global community attacked it from every angle. Weak evidence was identified as weak, and the solid discoveries, the methane, the carbon dioxide, the water-rich interior, survived every single challenge and came out stronger on the other side. That is not science failing. That is science working exactly as it was designed to work, in public, in real time, on the biggest question there is. The planet did not get less interesting when the headlines faded. It got more interesting. Because now we know precisely what we are looking at. A warm, water-soaked world 124 light-years away, still holding its deepest secret behind a curtain that we already have the tools to open. The light carrying the next answer is already on its way. It left that alien sky before anyone alive today drew their first breath, and it is streaming into a golden mirror 1,000,000 miles above your head at this very moment. The only question left is what it will say when we finally learn to read it clearly enough. If this is the kind of story that keeps you staring at the sky a little longer than you should, subscribe right now and turn on notifications, because when the next results from K2-18b drop, this channel will break them down before anyone else. Drop a comment and tell me what you think. Is that ocean empty, or is something drifting through it? Something quiet, something ancient, something waiting to be found? And share this with someone who still thinks the search for life beyond Earth is science fiction, because the truth is, it is a measurement we are already making.